Hello everyone, my name is Siddaarth,
My name is Pratham.
My name is Nisheet.
and today we're going to be talking about our homemade alternator. So first of all, what is an alternator? Alternators just convert mechanical energy into AC current. You might have heard of generators, which are very closely related to alternators, but the difference is generators can produce both AC and DC. And so the way an alternator works at its core is you use mechanical energy to cause some sort of change in flux, and that change in flux will cause an EMF. So in the picture below, you can see that the actual coil is being spun while the magnets stay in place to induce an EMF. So now let's talk about the engineering process a bit. So first, let's look at the design plan. So the aim of this project was to create, a simplified alternator. And our first plan, you plan to have two rotors spinning with four coils between the gap. And by having two rotors, the change in magnetic flux is greater, which increases our efficiency. And we wanted to minimize friction of, whatever we're spinning. So we decided to use bearings, but rather than buy new bearings, we decided to reuse, fidget spinners, which are pretty, some people are common, they're found around the house and salvage the bearings out of those. And we initially planned to make it out of wood, but we moved away from it. And then something with alternators is they produce AC current because if you look at the design on the first slide or the slide, notice that the direction of flux change will change every turn, and because of that, the current will be in AC. So to convert AC to DC, we use a diode bridge rectifier, which you can see in the right hand diagram, and it using diodes which are one-way switches, it'll just turn the AC into DC usable DC current. So here's a very early draft of our plan where we had rather than using wood, we're going to use 3D printed mounts. We have bearings, and we have a rod which supports, two rotors of magnets. And in the middle, we have our coils, which is, what will actually generate the current. So here's our, real ones. So here are coil holders, which sit in the middle. Here's our two pairs of magnets, and, here are our mounts. And here's the threaded rod that we use. We use mounting tape or masking tape to friction fit it into the bearings. And here's a diode bridge rectifier, which takes AC, which is, supplied in these rails, and turns it into DC, which is both these are two separate orange wires. They're the same color, which makes it confusing, but this is our DC power supply. Or not power, it's our DC output. So now let's talk about the design components. So for the rotor, this would be catted this, and we would basically just it would have to house two magnets in between each rotor, and rather than glue our magnets in, we would friction fit magnets using tape around the sides. Now for the coil holders, we started off with a very old, like bulky design because our catting skills are, not that great. But the issue with this is that it had a lot of bulk, and the design had a lot of plastic, which meant that the gap between the coils and magnets would be relatively high, and that leads to much lower efficiency. So we ended up using Tom Stanton's coil designs and modified them to our needs. And these are much thinner and increase our efficiency significantly. And you can see these new ones. So some issues, one of the, on top of the issues we had before, one issue we had was that with wood, we could not, drill holes to fit the bearings in. So we decided why not 3D print our own. And so our first mounts, did not have enough material on all sides to sustain equally biaxial loads. And all of them broke after some period of time. And so we had to redesign them, and we added a lot more material on the side, as well as increasing the infill and the wall thickness. And this gave us a much more robust mount that is able to, withstand any loads it needs to. So now let's move on. Nisheet will talk about, our discussion and calculations.
Again, the aim of the project is to create a simplified version of an alternator, taking advantage of the semi-conservative properties of magnetic fields to generate a voltage difference capable of powering small electronics. We built it using 3D printed magnet wheels, coil holders, and stands, and copper wiring and neodymium magnets were integrated into the coil holders and wheels. It was capable of charging a capacitor reliably, and we measured the discharge rate of the capacitor. We charged to various voltages over 5 trials using a multimeter and a timer. Physics tracker was used to measure the RPM of the magnet wheel and correlate that to voltage we were generating over time. One source of error was fitment issues. Strong magnets were problematic because when they put close together, they would attract or repel each other. In addition, the firmness of the coil holder sometimes led to unwanted friction between the spinning wheels. In addition, copper cables had a lack of affinity with the bedrock rails and were very loosely connected, and they would get yanked out if a stray cable hit the spinning wheel in the wrong area. In addition, spinning the alternator with our hands would lead to a lot of human error because the wheels wouldn't spin at a constant speed. And if we slipped our hands, then we of course couldn't spin the wheel. Many sources of error would be like mitigated or eliminated if the structure of a product was more streamlined. And we also added more coils and coil holders since the voltage is directly proportional to the number of coils. Now, our product is capable of producing an average of 10 millivolts at its highest RPM, which seems small, but we are able to charge a capacitor to around 600 millivolts within 7 seconds. I won't read the full procedure due to time, but essentially we just measured the potential difference across a capacitor using a multimeter, and then using tracker, we were able to graph it. And so using a video camera, we were able to graph it. Using Kirchhoff's loop law, we proved an RC circuit where we just did negative Q over C minus resistance times current is equal to 0, and then used integration to get the voltage is equal to initial potential difference times e to the negative T over resistance times capacitance. As you can see, our graph does very much resemble A times e to the negative x1 over b, where a and b are constants. We were able to achieve high R squared values ranging from around 0.93 to 0.97. There's very clearly a strong relationship between the potential difference across the capacitor and e to the negative t over b, as shown by the R squared volume. And this reinforces our earlier derivation, which claims that potential difference is correlated with e to the negative t over RC. And this thus reinforces and proves both Kirchhoff's loop law and also capacitance, since it matches the voltage dissipated across by a capacitor, which used the formula Q over C. This is the magnetic flux data collection procedure, and where we essentially just got the peak voltage difference after spinning the magnet wheel.
Now on to the proving magnetism section, or more specifically, how magnetism has to do with voltage production. So we found out that our contraption gets around 10 millivolts and spun around 1020 degrees per second, or 170 RPM. And we reverse engineered this correlation between the RPM and the voltage generated to find out that the magnetic flux in the alternator is around 5.3 times 10 to the negative 3 Webers per second, where Weber is the SI unit for flux. Now going on to our assumptions, limitations, and implications. The main thing that we assumed was our alternator and all of our circuits were ideal. Moving on to our limitations. The first was that there was a large gap between our coils and our rotors in order to allow it to spin. The short version is that the intended distance between our coils and the rotor was actually 5 times less than what we actually had to spin it at, which resulted in 25 times less voltage being generated. For some more limitations, there is friction between the flywheel and the coils, resulting in a capped speed that we have to spin the alternator at, and also coil tangling, which was mentioned before, where a coil could get yanked out or a wire could get yanked out if it hits the alternator at the wrong point. As for implications, this will be elaborated in more detail later, but it's just that to engineer future projects like this, we need to engineer them and design them with more tolerances in mind, So even if we perform the input of the project at a less efficient level, the output will not be severely affected. Now for our results, Siddaarth will play the video. And as you can see in this video, all we're doing is we're charging up the capacitor as we're spinning our alternator. And in the real world, our capacitor can be used to do a myriad of things, such as make up for a loss of voltage in a circuit, or even absorb back EMF from a motor. So for our inductor conclusion, the main takeaway that we got from this was that conceptually an inductor would work for our project, allowing us to make up for any voltage losses while the alternator was spinning. However, while we tested it, we did not see any actual benefits for our homemade inductor, which is seen in the bottom right. So the conclusion was that although an inductor would work conceptually and even be ideal in a real-world scenario, it does not work experimentally, and the benefits it provides is either negligible or non-existent. As for our justification, these are just our various justifications that we arrived to with the help of physics laws and principles. And this is another fun application that you can pause and read if you want to. So some key takeaways, there are two really big ones. The first is that from an engineering perspective, as mentioned before, we need to design this such that the tolerances are high so that our product can still perform at its highest possible capabilities, even though we might not be efficiently performing it with our human hands or human input. And as an overarching takeaway, we need to curb expecting certain results. Yes. Moving on. This is our art aspect. Thank you for listening to our presentation. Wait, what are we at now?
Make sure to include the next slide as well. Just like.
But I mean, I talked, it's fine. We can attach the slide.
Yeah, we can.
Yeah, also, I think I like kind of misspoke in the beginning. Like, you know what, like I said, like, oh, like in the procedure, there, just like edit, just like cut that out. Like don't cut the entire thing out, but cut the part where I start cutting.
Yeah, I will go through it and cut stuff. I mean,
And
I'll
then
do it in the
also